This video is about the complex numbers. Complex numbers are actually a set of numbers that encompass the real numbers and the imaginary numbers. So complex numbers are going to be of the form a plus bi, whereas a real number might just be the a value, an imaginary number might just be the b value. A complex number is a combination of a real and an imaginary part. So when we look at a complex number, we're looking at a number that has a real part and an imaginary part. But in order to first talk about that, we need to know what an imaginary number is. An imaginary number is a number that when squared gives a negative result. So by definition, the square root of -1 is the imaginary unit I, so that when you square it, you get -1. A complex number is going to have a real part and an imaginary part. Now keep in mind that complex numbers also include things like 3 plus 0i, which is of course just the real number 3, or 0 plus 2i, which is really just 2i, the imaginary 2i. So remember that complex numbers include real numbers and imaginary numbers and combinations of them both. So we first want to be able to simplify things that have negatives underneath the square root. So let's take a look at these examples. Trying to straighten it out. Okay, so we're going to take a look first at the square root of -49, which is the square root of 49 times -1. And because of our rules of exponents, we know, or not exponents, but radicals, we can take the square root of each piece of this separately, and we'll get the square root of 49 is 7, and the square root of -1 is I. Similarly, we can take the square root of -180, but -180 is not a perfect square. So I do want to think of 180 as a product of its largest perfect square factor. So I'm going to think of 180 as 36 times 5. So I'm going to rewrite this like this, and then take the square root of each piece. So the square root of 36 is 6. I cannot take the square root of 5, so I will leave that there. And the square root of -1 is I. I prefer to write this as 6i root 5 just because it seems cleaner. Okay, one more example. This negative's on the outside of the radical, so it doesn't really matter to us except that we'll tag it on. But let's think of 32 as 16 times 2 because 16 is a perfect square. So we have 16 times 2 times -1, and then we'll subtract 2. So in this case, we're going to get negative. Square root of 16 is 4. Square root of -1 is I. Root 2, because we can't take the square root, and then we will subtract 2. So our final answer here was minus 4i root 2 minus 2. So we call these complex numbers, but working with these is really not difficult. We want to be able to add and subtract, multiply and divide these. And when we're adding and subtracting, basically we're just going to add or subtract the real parts separate from the imaginary parts. So in this particular case, these parentheses don't really mean anything to us. I'm just going to drop them. And we add as if they are like terms. So 3 plus 5 are the real parts. We get 8. And then we get minus 4i plus 6i, which gives us 2i. And we have added that. Just add the real parts and add the imaginary parts. Now we have to be careful with subtraction because in this particular case, the parentheses do mean something, and we need to distribute this negative sign through the set of parentheses. And then adding will give us negative 2 plus 11i. That is how we add and subtract complex numbers. We also want to be able to multiply and divide complex numbers. Multiplication is a little easier. Basically, we're going to use the distributive property or the FOIL property, and we just have to remember that I squared is negative 1. So anytime we see an I squared, we're going to replace it with the negative 1. So starting with this first example, we're just going to distribute this 5 through, and we'll get 5 times 3, which is 15. 5 times 7 is 35i. So simple distributive property there. We're going to do the same thing here. We'll distribute the 5i, so we'll get 30i minus 20i squared. And then we have to remember that this I squared is actually negative 1. And if we write this in the what we call the standard form, the real part and then the imaginary part, we're going to get 20, positive 20, plus 30i. This last example is a little bit more difficult because we have two binomials, but we know that when we have a binomial, we're just going to FOIL. So the first 5 times 4 is going to give me 20. Outsides will give me 30i. Insides, negative 36i. And the lasts, minus 54i squared. So simplifying, we can add our like terms, negative 6i, replacing our I squared with negative 1 gives us 20 minus 6i plus 54, or 74 minus 6i. So multiplying and dividing, we're just going to distribute and or use the FOIL property and replace I squared anytime it appears with a negative 1. When we divide complex numbers, we are going to have to multiply, but we multiply by something called the complex conjugate. So when you have two conjugates, something like a plus bi and a minus bi, what happens when we multiply those is we get a squared plus abi minus abi minus b squared I squared. And I think you can see that these two terms add to 0, and we actually just get a squared plus b squared. So notice that we do not have any imaginary part of this result. And that is why we multiply by the complex conjugate. So looks like this one got a little on the wrong side, so let me move this over. get rid of this here. And let's take a look at how we would divide these complex numbers. So because we don't like to have a radical in the denominator, and an I is actually a radical, we want to make sure that we don't have an I in the denominator. So to fix that, we are going to multiply by the conjugate of the denominator. So in this case, 4 minus 5i and 4 minus 5i. So the number that we're multiplying by is actually 1. It's just that on the bottom, when we multiply it out, we're not going to have an I down there anymore. So when I do this, on the top, we're going to get foiling 12 minus 15i minus 16i plus 20i squared. On the bottom, we'll get 16. We know that the insides and the outsides are going to go away, so we're going to just multiply the last two, which was minus 25i squared, or plus 25. So we end up with 41 in our denominator minus 31i, and 12 minus 20 is going to give us minus 8. So let's do that again on this next one. I should be multiplying by the conjugate of the denominator, 7 plus 2i. On the top, we'll get 14 plus 4i squared. 14i plus 4i squared. On the bottom, we'll get 49. We don't have to worry about the insides and the outsides. And we'll get minus 4i squared, or plus 4. And our result here is minus 4 plus 14i over 53. And again, our only goal is to get the I term, because it's a radical, out of the denominator. So on this last one, because our denominator is not a binomial, we can just multiply the top and the bottom by I. We don't have to multiply by minus 5i, because all we're looking to do is make the I into an I squared. So this is going to give us 5i minus 4i squared over 5i squared, which is 4 plus 5i over negative 5. And I'd just like to make a note, I didn't think to say anything earlier, but you'll notice instead of writing I, that I put a little hooky-do on my I, and that's because if I'm not careful, if I don't make my dot of my I very good, it can look like a 1. So you might want to consider putting that little hook on your I like that, so that you remember that it's an I even if you can't see the little dot. All right. Okay, the last thing in this section is powers of I. So we already know that I is just I. There's no reason to write it any other way. I to the first. And that by definition, I squared is negative 1. But if we have a power of I that's higher, like I cubed, we can of course think of it as I squared times another I, which in this case is negative 1 times I, or negative I. I to the fourth we could think of as I squared times I squared, which is -1 times -1, or just 1. We really like this fact, and we'll use that in just a moment. And then what you'll notice is that after I to the fourth, things cycle through. So I to the fifth would be I to the fourth times one more I, but I to the fourth is 1. So what we do when we want to evaluate a power of I, let me get rid of this here, it's from this other, I don't know why these are coming down on the other page, but they are. Okay. What we want to do is divide, basically, by 4, because I to the 45th is actually I to the 4th to the 11th power, because that's 44, and then one more I. So this is really I to the 44th times one more is I to the 5th. Well, we know this is just 1 to the 11th times I, and we get I. So the shortcut way to do this is to take our 45 and divide by 4. We know that's 11. And we get 1. So as a remainder. So I to the 44th is the same as I to the 1st, or just I. So similarly, if I divide 18 by 4, I'll get 4, which is 16, and the remainder is 2. So I to the 18th is the same as I squared, which is -1. For this last one, we can use our rules of exponents and say that this is I to the 5 plus 3 plus 4, which is I to the 12th. 12 divided by 4 is 3, with a remainder of 0. So I to the 12th is the same as I to the 0, and we know anything to the 0 power is 1. So the idea here is that we divide our power by 4, and what we're interested in is the remainder. That concludes this video. See you next time.